Hello, my name is Zhenbin Wu from UIC. On behalf of the CMS Corporation, we'll talk about detect new physics with deep learning trigger at the LHC. So the LHC have a big data problem. At 14 megahertz trigger rate, we recording about 1 petabyte per second data. With zero suppression, we reduce to 20 terabyte at the rate triggered by 100 kilohertz at the level 1 trigger system, which consistent with the local instruction using FPGA. And further, we reduce the trigger rate to 1 kilohertz with the HLD form, which is a CPU form, and reduce the trigger rate, data rate about 1 gigabit per second. And further on, we have a local reconstructions with the offline computing and perform the data analysis on it. At the end, we achieve about 100 paper per year, about 110 megabit rate. So to handle the large amount of data, we explore the trigger system at the LHC. Fortunately for LHC, the intrinsic physics process tend to have a smaller production cross-section comparing to the elastic productions. So we call this finding needle in a haystack scenarios. And actually we did it. We found the Higgs boson from all the haystack we have. With the trigger system, the event that not trigger will be lost forever. So in a nutshell, the solution to the LHC big data problem is the dramatic data reductions. But then people worry, could the new physics have been discarded at the trigger level already? This is because traditional new physics search rely on the hypothesis testing with the specific alternative model, which means you study the hypothesis by designing your trigger on the trigger level, and then select the events, and then further perform search based on the selected events. So this also motivated multiple attempts for model-independent searches at high-level trigger system all over the years. So the idea is that whether or not we can have a model-agnostic trigger that just trigger for anonymous events using the tool of deep learning. On the left-hand side, you can see that with standard trigger, you calculate a variable which is sensitive to your signal, and then you try to keep your trigger threshold as low as possible, which can trigger the event containing the background or interesting signal in your trigger stream. And further on, you perform the analysis and then have a signal region where you achieve a better signal background ratio, where you can select the event for search for new physics. The idea is that with the deep learning, you can construct an X variable, any variable in higher dimensional variables that you could already sensitive to the new physics or other events in this distribution, where you can directly trigger on it, so you can achieve a better selection efficiency. And this kind of trigger should be deployable at the level 1 trigger system to avoid any bias from the upstream. And of course, it should need to be within the resource and latency requirement of the trigger system. So we explored the autoencoder as one of the model in this study. So autoencoder is a compression decompression algorithms that learn to describe a given data set in terms of the latent space, which is 4-dimensional to the input. And from the latent space, it further reconstruct the original events. And so by this encoder and decoder scenario, you compare the difference between the input and output, calculate as a loss functions. So by minimize the loss function, you will be able to capture the feature of the training data set. So this is considered unsupervised learning that the autoencoder can be used for data compression, generation, or clustering. So in this scenario, we can define the anomaly event that is any event that where the decompressed output is very far from the input in terms of the reconstruction loss, in which we can use the reconstruction loss as the threshold for triggering. So CMS is have a preparing for phase 2A. Here is a skeleton for the upgraded CMS phase 2 level 1 trigger system. So we have a calorimeter trigger, muon trigger, and a chat trigger. We combine and send the information to the correlator sessions, where we can produce the particle flow candidate by combining the information from calo, muon, and track, and vertex informations. And further, we can provide the puppy weight of all the input particle, which can use for the pilot mitigations, and the candidate which is the event selection will happen in the global trigger, and all the output of the trigger system will send further to the lower stream. So here is an example autoencoder model. We train with a simulated zero bias event at 200 pileup using the simulated puppy jet, MAT, and MHT. In total is 18 input variables with certain pre-processing to enhance the performance. And this model will have the intention to be implemented at the global trigger system. So the model is constructed with the ReRU as an activation function, and then we pick the L1 loss function as the loss function in the training, in total of A layer deep. So as you can see that the model is designed with simplicity in mind, because we pick them to be easy to implement in the firmware, and also with the requirements, we need to keep it as simple as possible. So during the training, we only train the model and validate it with the simulated zero bias events without any knowledge of the signal during the training. And we use the reconstruction loss of the input and output as a discriminator, use it to influence on the signal sample. From the diagram here, you can see that even though agnostic to the signal, the autoencoder can show the separation power from the zero bias events for all the various models. You can see that at 100 kHz, you can reach 20 or 60% selection efficiency already with signals. So to implement the autoencoder using the HLS4ML package, which can transfer the model into firmware to be implemented in FPGA. Additional to the HLS4ML package, we wrote additional logic for the L1 loss function calculations. The autoencoder was fully unrolled with minimal latency, which is well within the phase 2 global trigger latency budgets. We implemented with the Xilinx Ultra Scale FPGA as a VNIP chip. The autoencoder consumes about 10% of the DSP resource and about only 1% of the flip-flop and lookup tables. During the study, we found out the autoencoder is not sensitive to small variance of individual input feature. That means that you can tolerate the noisy online conditions. So there's a scenario that if the autoencoder trigger rate can rise above a fixed budget, this can be still prevented by adding additional logic in the firmware that could dynamically adapt the trigger threshold of the autoencoder. So we can have a fixed trigger rate from this autoencoder if the online condition getting worse or unstable. So in conclusion, the LHC have an enormous potential for discovering new physics beyond the standard model, and with the unprecedented collision energy and large production mechanisms. And we propose a model-independent anomaly detection technique based on deep autoencoder to identify new physics events. So we showed that a simple autoencoder model can be implemented at the level 1 trigger system. There's more advanced autoencoder model that can be designed for the next level, the high limit, the HLT, or even the 40 megahertz scouting system. So this study has been documented in the CMS Phase 2 TDR. So stay tuned for the upcoming release of the CMS Phase 2 Level 1 Trigger TDR. Thank you for your attention.